Hello everyone, I'm Zhao Wang from the Chinese University of Hong Kong. I'm glad to present our paper of efficient transferability assessment for selection of pre-trained detectors. This work is in collaboration with Aoxue Li, Zhenguo Li, and Qidou. As we all know, there are lots of pre-trained models available, so selecting a good one for a downstream task is very crucial. However, brute forcefully fine-tuning all models for selection is accurate but very costly. Thus, how to select a model where assessing the transferability is important, which is very accurate and efficient. There are some methods existed for evaluating the transferability of pre-trained models. For example, the logarithm using the evidence, and the SFD proposed a self-challenging fine-tuning strategy. However, these frameworks still suffer from assessing the transferability for pre-trained detectors. Thus, we further propose a simple yet effective framework for assessing the transferability for object detectors, named logarithm. Here is the overview of our proposed framework. To do this, we build a detector transferability benchmark. First, we construct a detector zoo composing of 33 different pre-trained detectors. These detectors are trained on different schemes, such as supervised or self-supervised, and trained with different datasets, such as COCO, Open Images, and ImageNet. Also, the detectors are from different types, such as two-stage based or single-stage based, and transformer based, such as data DETR. Also, they are equipped with different babbles, such as ResNet, ResNext, and RegNet. Also, we adopt 5 datasets from 5 diverse domains as our downstream tasks for evaluation. Also, we use the weighted conduct tool as our evaluation protocol, which is evaluating the ranking correlation between estimated transferability scores and the ground truth fine-tuning performance. The equation is shown here. Also, we adopt another top one relative accuracy to measure how close model with the highest predicted transferability performs in terms of fine-tuning performance compared to the highest performing model. Then, we propose a series of detection model transferability metrics. First, we try to adopt the log mean as a basic metric. To evaluate the transferability, we first extract multi-scale object-level features of ground truth boxes via pre-trained detectors bamboo with ROI align layer and connect the object-level features to form the feature matrix, 4-dimension coordinates, and class labels. Then, with the evidence theory and the basic principles in graphical models, we can measure the transferability by using the maximum evidence, and shown here. Here, W is the parameter of the linear model, and alpha and beta denotes the parameters of prior distribution and the posterior distribution of each observation. And then we finally optimize the W to obtain the solution of weight M. Then we can use this equation to compute the maximum evidence as the transferability score, which is the basic score for our detection metric. Then, however, there are many issues with the basic logarithm, because, for example, it cannot tackle the multi-level features. So we propose pyramid feature matching to help each object find the match level PL and apply the bounding box center normalization and joint coordinates evaluation to improve the effectiveness. Then, inspired by the nature of the detection, we unify the bounding box coordinates and the class label in a unified label, YU, and evaluate the transferability as a new metric which is named U log me and shown here. Then, however, such MSE-based evaluation is not robust to object scales, while the IOU metric is good at tackling such issues. So we further introduce a complementary metric named IOU log me by measuring the IOU between the prediction and ground truth bounding boxes. Finally, we want to combine the advantages of the U log me and IOU log me because IOU-related evaluation is robust to object scales, and the MSE-based evaluation is sensitive to measure the absolute difference when the two inputs have no intersection by addition with the hyperparameter mu. Then we come to the experiment section. Here is our experimental materials. For the datasets, we adopt 6 downstream tasks, and for the evaluation metrics, we employ weighted confidence interval, top 1 relative accuracy, weighted Pearson coefficient, and the top 1 recall. As for the transferability metrics can be unstable, we randomly sample 22 models from 33 pre-trained detectors and use 1% of the 33 choose 22 possible source model sets for measurement. And our comparison methods are from the previous SOTA conferences. Here is the main result of our method compared with the state-of-the-art methods. We can learn that our method achieves the SOTA performance and performs better than the previous SOTA methods such as KNAS, SFD, and logme. Then we do some analytical studies. The first one is we visualize the detailed ranking details, and we find that with our improved metric, our metric can better ranking the different detectors as shown here, and with much higher weighted confidence interval, the ranking correlation. Then we study each component in our proposed framework. We can see that each component does have a contribution to the final performance. Also, we study the different bounding box normalization techniques, including the border normalization and center normalization. Also, we perform analytical studies on the different weights for complementary IO metric. We can learn that with the complementary IO metric, that logme always performs better than basic logme and U logme. Finally, we conduct the efficiency analysis of our framework. We evaluate the efficiency from 2 aspects. The first is the work clock time, which indicates the average time of finetuning or evaluating of 33 pre-trained detectors, and the second one is memory footprint, which indicates the maximum memory required during finetuning or evaluating of 33 pre-trained detectors, including the loading of visual features and the computing transferability metric. We can find that our method reduces work clock time 32 times and requires a mere 5.2% memory footprint compared to brute force finetuning of all pre-trained detectors, which indicates that efficiently assessing the transferability of pre-trained detectors is very crucial and important and essential task for the downstream tasks. That's all for my presentation. Thanks for your listening.